Hello, it's Keith here, and this is lesson 106 of the platform-specific series of my Z80 assembly programming tutorials. Now, we've been covering Maxtile recently, which is my multi-platform software tilemap code, and today we're looking at the MSX1. Now, the MSX1, of course, does have a hardware tilemap. We could be using this in tilemap mode, but that wouldn't provide the functionality that Maxtile requires. Maxtile works in the same way in every system. It provides Xflip and Yflip, double height and filled tiles. So that would be quite difficult to do if we were using the MSX1 in tilemap mode. So what we're doing is we're using the bitmap screen mode. This is where basically the screen uses a different set of patterns for the 3/3 of the screen, so that each third can use a different 256 tiles, giving the full 768 required for every pixel on the screen to be controllable independently. So that's what we're using here. You can see we've got some test characters around the screen. So these are simulated sprites, so they're actually being drawn with the tilemap as well. We can do our Xflip and Yflip. You'll notice there's some glitching in the colors here. This is not because of bugs in the code. This is simply because I did a very crude conversion using my Sprite editor to create the test graphics you can see here today. They haven't been properly converted. That's why you've got those glitchy colors. So that's what we're going to be looking at today. Okay, well, let's go over to the code and let's see what we've got. Okay, so here is the code. So the example we're running today is MSX Maxtile mid, and then the graphics routine that's doing the individual tiles is the MSX1 V1 Maxtile normal. Maxtile, a lot of the code that handles the tilemap data, working out what tiles need redrawing and the moving of the sprite objects, is multi-platform code, which is covered in a separate series, and we're not going to be mentioning it today. All we're going to look at today is the code that handles the drawing of the tiles to the screen within the bitmap area. Okay, so we've got some initialization data up here. Now, Maxtile uses 3 caches for the 3/3 of the screen, which is coincidence. It was designed for the Amstrad CPC, and you could sync these to reduce the amount of flicker. So we've got those here again today. We've also got a 256-byte lookup table, which is used for the Xflip effect. We're actually doing pixel data here, calculating in real time the Xflip equivalents. So that is what we've got there. We've also got the base of the screen. Now, because we're using the pattern data for the bitmap screen, the VRAM base is a quadruple 0 for the top left corner of the screen. So that's why we've got that there. We're defining the dimensions of our screen in logical units. Logical units is pairs of pixels in my tutorials every time. We have this weird thing here, which is a macro called MSX1 no-op. Now, this is because on the MSX1 VDP, we actually have to delay a little bit between each write to the VDP. The MSX1 VDP was a little bit slow. However, if we're actually using an MSX2 piece of hardware for our MSX1 style code, our MSX1 video mode, we actually don't need that in operation. I believe the VDP was heavily upgraded, so it was much faster. So if you're only wanting simple graphics but are using an MSX2 only, then you can remove that no operation. So just change this macro, and that will speed up the execution of the code, but it won't work on a true MSX1. Unlikely to want to do that, but I thought I'd leave it in as an option. Okay, now our pattern data is down here. This is the pattern data that we're using here. Now, we're using black and white graphics in a sense, so in theory, each 8x8 pixel tile pattern should be 8 bytes. However, each tile pattern also has a separate 8 bytes that defines the colors. So, like the CPC, we're actually using 16 bytes for our tile and pattern entries here, although in a very different way. The CPC is 4 colors, whereas the MSX1, I guess you could call it 16 colors. I'm not sure. It's a bitmap data plus 1 line color attribute, so very different to that system. But anyway, so we've got our data aligned here so that the tile numbers match the ones being specified in the miniature tile maps that define the simulated sprites there. They're actually miniature tile maps as well. All the graphics drawing is done by the same tile map code. Now, apart from the pattern data, we also have some special fill patterns which have a slightly different format. These use 2 bytes repeated for each line of our pattern. You can see those at the top of the screen if we just restart the example here. So if we just wait a moment. So these here are being drawn without those filled patterns there. And so these use 2 bitmap bytes here, followed by 2 color attribute bytes here for the alternate lines of our pattern. So that's what we've got there. Now, at the start of our code, we're doing a couple of things. Firstly, we're setting up the screen. We're configuring the VDP registers for the screen that has 768 unique tiles. because the screen is in thirds and each of those thirds uses a different 256 tiles, we need to fill those with consecutive numbers from 0 to 255. And that's what we've got here. So we're writing 0 to 255, repeating 3 times, filling the tile map. The tile map starts from 1800 in VRAM. That's the only time we set this. We set this at the start, leave it well alone, and then we just change the pattern data, which is effectively our bitmap screen. So that's what's going on there. And as for our control registers, well, the ones you need to use for the bitmap screen in this configuration is these here. This will set the screen up in that mode. So that's what we've got there. The final thing we've got is the lookup table. So we're configuring the lookup table here. So this is taking an 8-bit black and white, effectively bitmap, and flipping the order of the bits, so the leftmost bit becomes the rightmost, and so on throughout the byte. Now, the lookup table, the bottom byte of the starting address is 0, and what we do is we basically use that as the byte we want to convert, and we shift all the bits, write the flipped equivalent at that address, incrementing L until we've done all 256. What this means is that if we load the top byte H with the address of the fliplet and then the L with the byte we want to convert, and then read in from the HL address, we will get the flipped equivalent of that byte, and we use that in our tile drawing, because as I say, effectively this is a bitmap example, even though the MSX1 is a tile sprite based system. So that's what we've got there. Now here is our actual example code here. So this is doing the drawing. Now if we're drawing the entire screen, we use that defined base in our that was defined as a reference here, screen base. So that is the VRAM destination for drawing the entire tile map. However, if we're just drawing a simulated sprite that's moving around the screen, we use the get screen pos command to calculate that. Now, the important thing to understand about the data within VRAM that relates to the patterns that we're going to be changing when we draw to our screen is that there's 2 parts, and each of those is 8 bytes. The black and white data starts at memory address quadruple 0. The color data actually starts at memory address 2000. We shift to the color data by ORing in 60. The VRAM destination isn't 6000 though, is 2000, and setting that bit 6 there, effectively adding 40 here, is defining this as a writing address. And so when we want to write to VRAM addresses starting at quadruple 0, we're ORing in 40 because that is defining that we're doing a write and not a read. If we didn't do that, we'd be reading, and this wouldn't have the effect we desired. So that's how our VRAM actually works. And the long and the short of this is what we're doing here is we're converting from our logical unit pairs of pixels coordinates in X and Y coordinates into a VRAM destination. Now what we're doing here is we're effectively multiplying our X position by 8 here, because there's 8 bytes per pattern, per tile, X coordinate tile, and then we're taking our Y coordinate and effectively multiplying it by 32, because there's 32 tiles on a line, times 8 because there's 8 bytes per tile here, and so that is effectively being done there, and that's taking our Y coordinate and putting it in H, our X coordinate multiplying it by 8 and putting it in L, after we've rounded these to a whole number of tiles, of course. So that's what's happening there. Now, our draw tile routine does the job of actually getting one 8x8 block onto the screen. Now, this routine is only executed if the update flag has been set. When this routine is executed, BC will point to the tile map data that is used by Maxtile. Now, Maxtile uses 2 bytes per tile pattern, and the least significant bit of those 2 bytes is an update flag. If that is 1, the tile needs to be redrawn. If it's 0, it does not. If it's 0, this routine will never be executed. If it is, the least significant bit will already have been shifted out of the accumulator, leaving these remaining bits in A here. So when we're testing bit 0 of A here, we're actually testing what was bit 1 of the original data within the tile map. Now, as I say, we know we need to draw something, because otherwise we wouldn't have executed this routine, and it's just a question of what we need to draw. Now, Maxtile works as a sort of binary tree, with the most simple common routine being executed the most quickly, and the more complex ones being executed after various comparisons, which will slow things down a little bit. So what we're doing here is we're checking if the program flag is set, and if it's not, then this is the most simple kind of tile, an unflipped tile. In the case of the unflipped tile, what we're doing is we're shifting a 0 back into the accumulator and writing that byte back to the tile map, effectively clearing the update flag. Now, what we're then going to do is we're then going to take the 4 most significant bits of the remaining byte, and that becomes the low part of the offset to the pattern we're using. On this system, like the Amstrad CPC that this was designed for, each pattern uses 16 bytes. And so by using the bottom 4 bits as various command bits, we've effectively pre-multiplied, if you will, our tile number by 16 here. So what we're doing here is we're adding DE, which is the offset to the start of the pattern data for our tile number, and this has effectively given us the source pattern address that we're going to use. Now we're using stack misuse here. It might not really be worth it because we're having to delay so much anyway, but it's convenient for working with the registers in some cases, so we're still doing it here. So we're loading the source pattern data into the stack pointer here. We're then selecting the VRAM destination, which was in the shadow registers H and L, ORing in 40 in hexadecimal here so that we select the right address. Now we're going to do the bitmap data first. So all we need to do is we need to take 2 bytes out of our source pattern data and write them to the VRAM, and we've got some delays here, and you can see the number of delays we have depends on whether we've done a pop DE or not, because the pop DE will take a couple of ticks as well. So this is writing all of the 8 lines of our pattern data to VRAM. Once we've done the pattern data, we now need to do the matching color data, which is in almost the exact same VRAM destination. However, we just need to add 20 to the top byte, plus the 40 to select the right address, so 60 in total. That is selecting writing, and so we're then going to do the exact same thing again, writing the color data to VRAM here. So that is doing the 8 bytes of color data. Once we've done that, we're finished. That's our tile drawn to the screen. Very straightforward, relatively speaking there. As I say, we've effectively got a bitmap screen here. Now, that's our most basic tile draw, which is the unflipped tile. Now, if the program bit was set, we're going to potentially do something significantly more advanced. So the first thing we're doing here is we're checking the X and Y flip bits. Now, if either of these are set, then we're going to continue on down here. But if neither of those are set, then this is what's known as a custom tile, which is our special code. This is double height, solid fill, and transparency, basically. But if we continue on at this point, then we're doing some kind of flipping. So what we're doing here is we're clearing the update flag, and then what we're going to do is we're going to, again, calculate our source pattern data here. So that's what we're doing here. And then what we're going to do next is we're going to consider the X and Y flip again and branch the appropriate piece of code to do this kind of flip. So we're checking the Y flip flag, and if that's not set, we know we're doing some kind of flip, so it must be an X flip we're doing. In that case, we're going to use the flip lookup table to do the conversion. We're loading this into the B register here, and then we are switching and selecting our VRAM destination here. We're doing the bitmap data first, and all we need to do to Xflip a byte is effectively load the C part of the BC pair with the byte we would like to flip, read in from BC, and then that is because of the way the lookup table was defined, that is the flipped equivalent of that byte we've just loaded into C. So this is effectively X-flipping our data, and we just write these to VRAM as before. This is the bitmap data we're X-flipping here. We don't need the no-ups anymore because we've got enough delays here anyway, so that's going to work fine. Once we've X-flipped the bitmap data, we do the color data. Now the color data isn't different per pixel within a line. The colors are just a foreground and a background for each line, so they don't need to be X-flipped, so we're just writing those as is. And so that's what we're doing there. And then we are basically done, and so we're returning here. So that's the X flip. The next option we're going to look at is the Y flip. So the Y flip, basically, right down the bottom I think it is. So the start of the Y flip, the first thing we're checking is if the X flip flag is also set, in which case we're doing an X and a Y flip. Now the Y flip works differently. Basically we draw the data to the screen in the same order from top to bottom, because that's the way the VDP works. Starts from a low address and goes up. So we're doing the data to the screen in the same order. So we're reading the data in backwards. So we're starting from the 15th byte of our source pattern data. So we're adding 15 to that source pattern data there to select the last byte. Now the last byte is the color information. So this time we're drawing the colors first. And so that's what we're doing here. We're just writing all those colors, moving backwards through the source pattern data as we do. Once we've done the colors, we then switch to the bitmap data. And again, we just transfer these to the screen, working backwards through our source pattern data. Pretty straightforward, really. And then X and Y flip, we simply do both tasks together. So we're moving to the last byte of the pattern data. We're doing our normal color data. We're just reading it in and writing it to the screen, moving backwards to the source pattern data. And then we use our lookup table to do the X flip, and we continue reading in backwards through our source pattern data, this time loading into C, reading in from BC, which is doing our flip because we loaded B with the lookup table's top byte address there. and that is Xflipping the data there. So yeah, pretty straightforward. Basically, as I say, the same as I've done on all of the other bitmap systems. So that's what we're doing there. The final kind of drawing is the custom tiles. Now there's 3 kinds of custom tile defined, because we're basically using 2 of the bits that were previously the low nibble of the tile number. So we're calculating our tile pattern address slightly differently. But basically we've got 3 kinds of custom tile here: solid fill, empty tiles and transparent tiles, and double height tiles. And we'll look at double height first. It's not very clever really. All we're doing here is we're taking our source tile number and we're effectively multiplying it by 16. Now we're actually going to only use 8 lines of our source pattern, but because each pattern has a block of bitmap data followed by a block of color data, we want to use half of each. And so that means basically shifting the memory addresses around a little bit. And so we're effectively multiplying by 16 here, whereas usually we'd probably only multiply by 8. But then what we're doing is we're checking if we want the odd or the even one. And if we want the odd one, we're effectively shifting 4 bytes down half of our pattern data. That's so that we use the second half of the bitmap data and the matching second half of the color data. So that's what we're going to do. Apart from that, relatively similar to before. The only difference is we now read in 2 bytes from our source pattern data. We're doing the bitmap data first, but then we write those bytes twice to the screen, so doing 2 lines with the same source pattern data. The double height was actually intended to save memory within the ROM cartridge or within the program code. So yeah, by covering twice the area with the same pattern data, we can save some source data memory. On a system like the CPC, it would also be a little bit faster, but on this system, because we're having to delay things, no, it won't be. Anyway, once we've done the 4 bytes of the source pattern data, making 8 bytes of the screen data, we then need to skip the 4 bytes that we didn't use, and so we pop DE twice. This now shifts us into the matching color data. So we now switch to the color data for this pattern, and we do the same again, writing the 4 bytes of color data twice to the 2 lines of the screen. So there we go, that's how we do our double height. Now our solid fill, again on the Amstrad CPC and systems like that, this would be much faster. We're only basically reading in a pair of bytes for our bitmap data and a pair of bytes for our color data. It's not faster on the MSX1 though, because we're having to delay things, so I mean it saves a little bit of memory, but again, most of the reason this is here on Maxtile is Maxtile has to work in the same way given the same source tile map on every system, so even if the benefits aren't there for one system, or if it gives disadvantages to that system, the system has to find a way of doing it, otherwise the program code won't work and I can't use this to port these games to lots of different systems. So here's the fill code. So basically we're multiplying our fill number by 4, 2 bytes for the bitmap data, 2 bytes for the color data, and then what we're doing here is we're simply selecting the bitmap data here. We're reading in 2 bytes and then writing them to alternating lines here. That's so we can give a nice checkerboard effect that gives us some flexibility with regards to how we use our colors and our patterns. And then we switch to the color data, read in the other 2 bytes, which are the color bytes, and write those to the screen as well. If you remember, we had 2 bitmap bytes followed by 2 color bytes here. So that's the data we're using there for that fill. Now the final one is transparency. Transparency doesn't entirely work on this system, but it does better than some. If you look at this character here, you can see around the wing and the hair there was a couple of lines that weren't filled in, whereas on this version there's a solid block around the character, but on this partially transparent one, if it comes back on the screen again so we can show it off here, you can see there's a few gaps around there that weren't filled in that otherwise would have been. Transparent tiles are also used for things like this Z80 character here. Around its feet there's some tiles that don't have any data and so are completely empty. Those are also transparent, if you can call them that, tiles, because let's say that's a tile block, that's a miniature tile map that's a rectangle shape. Some of the tiles are simply not drawn and they are considered transparent by this code. Now those completely empty tiles basically have a tile number of 255. So to test that, we increment the tile number read in. If it was 255, that becomes 0 and sets the 0 flag, in which case we just return. Otherwise, we're going to draw this transparent tile to the screen. Now, what we need to do basically is we need to multiply our tile number by 16 here to get the correct source tile pattern data. Now, the way we do things is we basically test the source bitmap data, and if that line is entirely zeros, then we consider this to be a line that should be transparent. So In the first case, what we're going to do is we select our bitmap destination here, we read in our byte from our source pattern data, and we see if it's a 0. If it's not, we write it to the screen, and you can see we do that over and over again here. Now, if it is a 0 though, we run this transparent skip byte routine here. Now, it's important to know at this point that this command here is a 2-byte command. And if we then take a look at what this transparent skip byte routine does, which is only executed if we want to not draw this to the screen, you can see what we're doing here is we're reading in from the VDP data port. Now this actually tricks the VDP hardware into incrementing the VRAM destination, so that the next byte that we actually write will write 1 byte along from where we did last time. So we're tricking the VDP into incrementing its destination counter there. We're then reading in the stack pointer return address, and we're basically incrementing it by 2 bytes and then writing it back and then returning. Now what this effectively does is it effectively skips the 2-byte out command after this call, so we're effectively skipping that out command. Now we could have done this with a large number of jumps to jump over these out commands. I think that would have been slightly faster, but it would have meant we would have had to have had loads of these in commands, and so I decided not to do it that way in this case. You know, it's up to you which you prefer to do, but I decided to do it this way, so that's the way I've done it. I think this saves a few bytes, so I think overall it's more memory efficient, but as I say, you're welcome to do it a different way if you prefer. Now, once we've done the bitmap data, we're then going to do the color data, but we don't compare the color data to 0, we're comparing the matching bitmap data to 0. So what we're doing here is we're reading the bitmap byte here, we're setting the flags based on that bitmap byte, and then we're reading in the color byte and writing the color byte if the bitmap byte was not 0. So a little bit tricky there, and I say a little bit slower. Again, the transparency effect isn't really very effective on this system. It's all about maintaining compatibility with Maxtile on the other systems for 2 reasons. Firstly, because if I want to port a game to this system that uses Maxtile, having a compatible version is essential. And also because the point of these tutorials is to try and do the same thing on a lot of different systems. And so, you know, while it doesn't make entirely sense on this system to do that, this is the way you would do the same thing as we've done on other systems. So that's the point of the tutorial. Now, as I often say with the Maxtile tutorials, you're welcome to take all of the code from my website and use it in your own projects, even if they're commercial. However, I suspect if you're at the level where you would want to do that kind of thing, you're probably going to write your own code anyway, and if you're not at that level, you'll probably find Maxtile too confusing. So what I'd suggest you maybe consider doing is taking the code that you've seen in today's lesson and just taking parts of it, even if it's just taking ideas from it and putting them in your own code, rather than using the whole of the Maxtile routines. You might want to just use something like the Xflip routines, for example, in your own code, because you could port those quite easily without worrying about the complexities of the rest of the Maxtile routines that it's going to take you an awful lot of work to understand. And as I say, if you're at that kind of level where you can do so, I think you're probably going to be aiming to write your own more tuned code to do exactly what you want and not waste memory doing more than what you want. But as I say, you're welcome to use it in any way you can. I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.